Patrick Rainey, and I take care of Northern California, Northern Nevada, and the Pacific Northwest as architectural specialists for W.R. Meadows. And frankly, we hope that the information we're sharing today will be helpful to all of you. So today, as Isaac mentioned, we're going to be talking about cold applied construction joint sealants, which play a critical part in building envelope performance. And this presentation is intended to explain the basics of joint sealants and introduce the options that are available. The intent really being to help specifiers and end users choose the correct product for the project. So the subtitle of this program is a critical part of the building envelope performance. And I think that's an important message in that I think we sometimes forget or overlook how critical joint sealants may be. They provide great protection in addition to our other systems, and also help provide structural protection so that the things we build and construct can perform and reach their life expectancy that they were designed for. So before we get into the presentation, for those of you who maybe haven't attended one of our previous virtual presentations or aren't familiar with us, a few things about W.R. Meadows. The W.R. Meadows company started in 1926 in Elgin, Illinois. Our company is family owned and operated to this day, and we're very excited that in just a few years, we'll be reaching our 100th anniversary. We're headquartered in Hampshire, Illinois, and we currently have 12 manufacturing facilities and 4 warehouses strategically located around North America. And that includes Blue Ridge Fiberboard, which is a part of the W.R. Meadows family and produces various sound damp proofing products. And in 2022, we acquired the Gemite company based in Canada, who we have worked with for many years already, and also opened our new innovation center in Hampshire, which is going to give us an even greater ability to work on product development and training. So we started with just one product back in 1926, which was asphalt expansion joint. And we now have over 300 products to help protect your design structures. So from our Division 3 offerings that include expansion joint materials to structural and surface concrete repair materials, epoxies and grouts to our liquids line that includes curing compounds, curing and sealing compounds, and sealers for decorative concrete. And of course, the joint sealant materials that we're talking about today. And then our Division 7 products, starting with underslab vapor retarders to air, water, and vapor barriers for above grade applications to our below grade waterproofing systems. So as you can see, we really have a full line of products to help in protecting the building envelope. Okay, there we go. So again, just a quick reminder, as Isaac already mentioned, this is an accredited AIA presentation, and all registered architects will be able to collect a learning point for it. So please be sure we get that information from you, including your name, email address, and AIA number, so that we can make sure you receive credit for the session today. So to take a look at our learning objectives first, we'll be looking at terminology, sealant purpose and applications, common problems that can occur, also joint design, as well as some of the factors involved that will lead us to successful installations, and also material selection. So as we proceed through the presentation, we'll take a look at each of these components. So just to take a quick look at the history of joint sealants, they were first used in prehistory, and people used whatever was available. Materials like mud, grass, and reeds. The next step forward introduced other materials such as pine and birch pitch, bitumen, wax, tar, etc., and a few other interesting items in there. Then a further progression in the 17th century when an early form of caulk was used to seal window glass. And by the 1920s, the first polymers were developed and used in sealants. So realistically, if we look at the timeline of developments in the 50s, 60s, and 70s, and up into the 90s, some of these technologies really are time tested and are still used, while some are relatively new. So when we talk about polyethers, for example, and STPEs that have been developed in more recent years, so a wide variety of products and many different technologies. So we can see from all of this how the technology has changed and advanced over time, and what these advancements mean to the construction industry today. So let's look at the purpose of joint sealants. Why do we need them? Well, they provide the critical line of defense for our structures, and many of these joint sealants provide that additional continuity we need to help prevent water damage, structural steel damage, reinforcing steel damage that can diminish our life cycle. And that also helps to prevent mold and mildew as well. So these products are used to seal penetrations in joints and also to help prevent water and moisture, as well as snow and ice from getting into our building's interior space. And if this occurs, a number of bad things can happen, including what we like to refer to as the M word, meaning mold, which is when the lawyers usually get involved, which of course nobody wants. So the further purpose of these sealant products is to accommodate movement, function as part of an air barrier system, as well as a vapor retarding system, and to contribute to acoustical control. So what we're trying to accomplish is to prevent water, air, vapor, and sound infiltration into our buildings, as well as gas and exhaust infiltration. So I want to take a few minutes to look at some of the common terminology that you're going to hear involving these materials and give you an idea of what these mean and how this can affect your choices when you're specifying these products. And you can see here what some of these terminology bullet points are. So first, let's look at the important distinction to be made between a caulk and a sealant. A sealant typically refers to a high-performance compound with better quality ingredients, polyurethanes, silicones, STPEs, polysulfides. With a typical service life of 10 to 20 years, great physical attributes, adhesion, flexibility, little shrinkage, excellent weatherability and UV resistant characteristics. While a caulk, on the other hand, is really a space filler, any low to intermediate performance compound. Typically lower quality with limited service life, usually 2 to 4 years. So if you have a small gap between your window molding and your drywall, and you want to fill it with something, you don't necessarily need a sealant. In many cases, it just needs a good filler. Then we have modulus. Modulus basically refers to the sealant's ability to absorb joint movement in expansion and contraction. Low modulus sealants are better at maintaining adhesion, are very elastic and can accommodate more movement, and they're generally softer. High modulus sealants at the other end of the scale have more limited movement capabilities, so they're well suited for static joints and glazing. But where we really live and breathe more often than not is right there in the middle. Most of our construction joint sealants exhibit a balance of adhesion, expansion, and strength, and are used for most of the applications that we're going to encounter. So we really deal with medium modulus products most of the time. But no matter what sealant you choose for your project, keep in mind that no matter how good the sealant is, it cannot overcome poor joint design or poor preparation or installation. Shore hardness is the ability of a sealant to resist penetration by a pointed object, like the heel of a shoe. Typically, low modulus sealants have lower hardness, and conversely, higher mod sealants have higher hardness. Now, this is not always the case. ASTM C661 is the standard test method for indentation hardness of elastomeric type sealants. And it's important to be aware that there are two readily accepted scales of shore. There's a shore A scale and a shore D scale. And you want to make sure that you're on the right scale when you're choosing your hardness ratings of your products, because the shore D generally represents the harder products. And a shore D of 60 and a shore A of 60 are not the same thing. So make sure when you're looking at these scales that you're on the right scale. Movement capacity is one of the most critical features, right? The ability to expand and contract with the movement of the joint. We want to make sure we know that our joint sealant matches the movement capacity of the joint that it's going to fill. ASTM C719 is the test method that addresses that movement capability and breaks down the 5 classes of movement. And these are plus or minus. So remember that we are not looking at a plus 25, we are looking at a movement of 25%. But from 12.5 up to a scale of 100 with a 50% recovery, which is what that dual number represents, are the different classes of movement. And again, we live in the medium. So the majority of sealants used in construction fall either into the plus or minus 25% or plus or minus 35% glass. The standard specification for elastomeric joint sealants, ASTM C920, has several test methods within it. And you need to understand that you can't just specify one or two of these. You really want to look at the overall picture. But they include movement capability, hardness, which we've already talked about, tack-free time, and then adhesion. And I want to take just a second to talk about tack-free time, because most of the sealants that are installed are single component and are climate dependent in terms of how fast they cure. So while there is a standard with ASTM C679 for tack-free time, the weather at your job site may influence the tack-free time and the cure time of your sealants. Some are dependent on humidity. Sometimes temperature makes a difference. Sometimes it's both. So you have to understand that what you see on the test specification, you may not necessarily get on your job site. So the testing standard for C920-18. Here are the different parts and pieces involved. This slide indicates the types, grades, and classes of joint sealants. Type S, well, what does that mean? Well, it means we are designing the type of sealant, a single component for type S, or if it's type M, that means it's a multi-component. So it could be a two-part, which most of the multis are, or it could be a three-part, but either way, it's multi-component. Grade. So in this case, grade NS means non-sag, typically used in vertical applications, or grade P, meaning the product is pourable or self-leveling, used in horizontal or flat applications. Class, which describes movement. In this case, indicating a movement capability of 35%. It could be 50, whatever that number is. It tells you what the movement capabilities of the sealant must be. Use. We have T1, T2, and NT refer to traffic grades. NT designates non-traffic. T1 and T2 are two different movement levels in the traffic grade materials. And then the use category referring to substrate materials. And it refers to substrates that these materials have been tested for. A is aluminum, G is glass, M is mortar, and O stands for other materials. So if you're going to specify a sealant, be sure to pick one that meets your needs. So we look at a spec, ASTM C920-18, type S, grade NS, class 35, use NT, and O. Well, this would designate a single component, non-sag, 35% movement sealant for non-traffic use that has been tested for adhesion to aluminum, but not glass or mortar. So this might be a sealant to use for glazing around aluminum fenestrations. So you know you're going to have good adhesion to those, but you're not going to glaze with it because it has not been tested for glass. So understand that when you're comparing products, this is your way to make sure you're getting the appropriate product. If, for example, you're looking at something that has, say, a class 25, but your spec is the one we are looking at in the example here, then it doesn't really meet the movement that's anticipated with your joint. So just make sure all the criteria meet what you're trying to accomplish. So we're going to take a look at just a couple of other terms that you're going to hear throughout the presentation. Joint interface, that's the sides of the joint where the sealant is adhered. And if you look at our illustration here, you'll see what we like to call the perfect joint. Sidewall adhesion on both sides, but the sealant will not stick to the round backer rod at the bottom of the joint. Well, that's just about perfect. And we will talk about backer rod more in depth a little later in the presentation. Again, you'll see on the sides, that's where the adhesion needs to take place. The same with the photo we have here. And that interface is important because we want that sealant to adhere properly. So there's also the consideration of three-sided adhesion. And it sounds simple to say, well, if we look at the photo on the right, I'm going to fill that joint and my sealant is going to adhere to all three of those points of contact, and it's going to be tightly sealed and never have any leaks. Well, the problem with that is we don't want three-sided adhesion. We want the bottom to be free so that when the substrate, in this case, those two pieces of concrete, expand and contract, the sealant can expand and contract as well. If the sealant adheres at the bottom, and in this case, we see an example of bond breaker tape, it's that black tape at the bottom there, which in this example will keep this from happening. But if we do have a situation where we get that three-sided adhesion, again, meaning that the sealant is sticking to both sides of the joint as well as the bottom, then this will adversely affect the ability of the sealant to move. So where do we use these products? Well, we could probably just say everywhere and call it good, right? Joint sealants are used in all types of construction and all types of locations, infrastructure, airport runways, highways. These are critical. You can't pour a long expanse of concrete on a highway and expect it to stand up without putting expansion joints in it. Bridges, sidewalks, obviously in commercial buildings. I've already mentioned being able to seal around penetrations and fenestrations in our building envelopes, expansion joints in our walls and our building structures, our parking structures, plaza decks. The applications really are endless. Joint sealants are used in all sorts of colleges, schools, prisons. Now, something a little bit different, wastewater and water treatment, where our sealant might be subjected to a submersible application. And there might be a need for special sealant for that sort of application. So you want to make sure you're using a product that is rated to be in the water. Or maybe it's a potable water situation. So a water treatment plant where we've got potable water and you want to make sure the sealant has that NSF 61 or whatever you might need in order to use it with potable water. Now, obviously, huge and tilt-up construction where we're creating concrete panels on the ground and lifting them up into place and then sealing the joints. And also the major retailing chains and big box stores. And then there's the warehouse chains and data centers. These are huge projects, right? Well, it's not uncommon anymore to see 1 million square foot plus with many of these. So how many expansion joints go into 1 million square feet of concrete slab? Well, the short answer is a lot. So there's a lot of joint sealant being applied. So what are the substrates? Well, again, basically everything. Concrete, brick, block, plywood, stucco, EIFS, changes in plane. Maybe it's concrete to aluminum. Maybe it's wood to concrete or wood to aluminum. So all of these different substrates, joint sealants are used. So you want to make sure, again, that you're choosing products that work with your substrate. And then, of course, the building envelope systems where they are used to seal penetrations and seal off fenestrations, and all those places where we want to maintain continuity of our building envelope system. So we have some shots here of these applications, changes of material, brick to aluminum, or maybe aluminum to stucco. Changes in movement in these products as they expand and contract differently. The sealants serve as that bridge to allow for those products to move independently without losing our watertight and airtight capability. Here's another example, in this case where the joint is sealed on the interior corner there, so it doesn't necessarily have to be different materials. And then the photo on the right, keep this one in mind as we move along here. It's regular expansion in a concrete slab, but notice the positioning of the nozzle and the sealant going in. And we'll talk about this a little more later on in the presentation. Also, precast concrete applications. On the left, we have a tunnel being built with precast panels, and the joints are being filled with backer rod before the joint sealant is installed. And on the right, a photo of concrete joints, a sidewalk to a building. That joint needs to be protected. We want to make sure that the sealant doesn't fail and allow water to get down between those areas. There's a little cut joint in the sidewalk there, which isn't truly an expansion joint, but there could also be an expansion joint there in the sidewalk somewhere that is also sealed. And then I mentioned plaza decks and sidewalks. Joint sealants are commonly used in these applications. And then here, swimming pools. First, we have a pool deck application where we can see the sealant that is above the water line, which is a pretty typical residential application. And further to that, maybe not in your typical residential pool application, but your commercial pools that often have an expansion joint at the bottom of the pool. And there are specialty products and sealants that are designed for those applications. So if you're doing that sort of work, you want to make sure that you're using the correct installation methods and the correct sealants. So before we get into choosing our sealants, let's talk about some of the issues that we need to be aware of and things that can happen that create problems. And the most common of these are adhesion failure, cohesion failure, and structural failure. So let's take a look at each of these one by one. So adhesion failure. This is where the sealant debonds from the sidewalls. Causes and remedies. Well, causes can be inadequate surface prep, and that's true of anything when we're trying to apply a material that we want to adhere, whether that be paint or a construction adhesive or something like a wallpaper adhesive. Without good surface prep, we're not going to get good success. So surface preparation is at least half the battle. Is it clean? Is it free of anything that might adversely affect our sealant? Improper installation. Is the product being installed correctly? And possibly in some situations, improper priming. So how do we address these issues? Well, grinding, sandblasting, saw cutting, all sorts of ways to create a good sound surface. And then cleaning that surface, maybe with a power wash and then an air blast to clean out the joint, works great. Proper tooling, making sure that we get that good joint interface so that our sealant adheres well to the sides of our joint, to the substrate, and proper priming. And we'll talk about that a little bit more, but primers can be finicky, and when we really want to make sure that we're using them properly and applying them properly to get the results that we want from them. So cohesive failure. This is different than adhesive failure. This is when the actual bead of sealant itself fails and tears down the middle. And looking at the photo here, you can actually see a couple of different circumstances. First, the wider joint on the right side, we see cohesive failure, where the sealant has ripped apart in the middle. And then if we look at the other joint running in the other direction, it looks like it's pulling away from one side. So maybe that's an example of adhesive failure. So what causes this? Well, again, improper joint design, or maybe we've got a joint that's too wide or too deep that we're trying to fill. Three-sided adhesion, and I mentioned this before, we want the sealant to be able to move in and out with the substrate movement. So obviously we want a proper joint design, the right sealant for the right joint, and then to make sure that it's installed properly. Lastly, we have substrate failure. A little bit different situation where maybe the substrate itself doesn't stand up to the movement. It isn't strong enough. Maybe the concrete wasn't poured properly. The design was incorrect. Or maybe there's been a washout or something that has occurred underneath the slab that's caused the substrate to be damaged at the edges. So how do we avoid this? What do we need to do in our specifications, in our material selections, to make sure that we avoid these situations? Well, for one, and we've mentioned this a couple of times, proper joint design, proper substrate preparation, the proper backing materials, and then choosing the material that fits the requirements of the joint, and then requiring a pull test, making sure that the sealant is performing as designed on the job in real life situations. So the standard recommended practice for creating the correct joint design, the rule of thumb is joint depth no less than 1/4 inch and no greater than 1/2 inch. If you're going any deeper than that, you might be extending the sealant beyond what it's capable of. With proper joint design, we are looking for a 2-to-1 width to depth ratio up to 1 inch in width. And frankly, that's about the maximum for a normal joint sealant. Most joint sealants will not tolerate wider widths. They just won't perform. So if you do need to get into wider widths and larger expansion joints, at that point, you might want to consider looking at some of the mechanical systems that are out there to seal your joint. So based on all this, if we have the proper 2-to-1 ratio, the depth is never going to be greater than 1/2 inch. Also consider the hourglass shape. If you look at the diagram on the right-hand side, the sealant has been tooled over the back rod, and you'll see right below the A on the horizontal section that the sealant is concave, which means that it's been tooled in, which actually helps to press the sealant down into the joint, flows around the back rod to give us that hourglass shape. And this also helps to improve our interface with the sides of the joint and gives us the maximum adhesion qualities that we're looking for. So that hourglass shape really gives us the joint design and configuration that we really want to see. Another thing to consider is the movement and conditions that can occur, and these take a little bit to think about, but a joint sealant at the lowest temperature will always experience compression. Now, I had a little trouble getting my head around this at first, but knowing that, let's just pick 50 degrees. If your substrates have contracted in the cold and your sealant is wider than it would be if it was very warm. So you fill the joint with your sealant, the temperature warms and your substrates expand, which compresses. So if the sealant is installed at low temperature, maybe it won't always experience compression, but the bulk of its life, it is going to experience compression. And conversely, if you seal something at the highest temperature, now your substrate has expanded, your joint has shrunk, maybe not visibly, but has shrunk a little bit. Your sealant goes in, the temperature starts to drop, and the substrate starts to contract. And now you're always feeling that extension or expansion of that joint. And that can be detrimental to the sealant. So for these reasons, many joint sealant manufacturers recommend not installing sealants in direct sunlight. And there are several reasons for that, but one of them would be that your joint, the substrate, is probably expanded. The joint is probably at its smallest, and you're always going to get that expansion pressure, which is going to affect your adhesion. So this slide, I think, helps to explain the strain that joint sealants are exposed to in substrate expansion, which occurs in warm weather. And we just talked about that, as well as contraction, which occurs in cold weather. So we have a couple of diagrams of that, looking at a situation where we installed on the left in an expansion condition and the sealant probably at high temperature. If you look at the joint design, the sizes are 1 inch wide by 2 inch deep, which is a very detrimental situation. Then we have 1 inch by 1 inch, which is not ideal, but in real life, a lot of sealants are installed at that 1-to-1 ratio. And then the preferred ratio of 2-to-1 on the bottom. And you look at the strain that's placed on the sealant. In the correct ratio, 32%. But in the opposite 1-to-2 ratio at the top, 94%. So basically, that's over 60% more strain. On the other side, if the joint is contracting, the strain is more than 12 times as much on the improper joint depth example versus the proper depth. Pressing that sealant up and out of the joint subjects it to damage, possibly from vehicles driving over it or foot traffic or anything else. So now we really have an issue of the sealant having a likelihood to fail, because when we open that roadway or surface back up to full service, if the sealant's been damaged, it may not continue to fill the joint. So this is a little review of joint depth. Depth must be sufficient to accept the backing materials, and in some cases, an expansion joint might be used with a backing rod. And we want to make sure there is enough room to get our sealant properly installed. The joint should be designed within the sealant's movement capability. And yeah, that might be true, but maybe the sealant should be chosen to meet the joint design movement capability. So maybe that should be conversely stated. The number and spacing of joints is critical, and that really falls on the engineer who's designing the system and is placing those expansion joints. We have been able to get to the joints. We have to be able to get to the joints. They must be accessible, obviously. And then there has to be sufficient bonding surface for the sealant. I know of a situation that one of my colleagues here told me about several years ago, where he was called out to a commercial pool application where the sealant had failed. And it turns out that the contractor had set the backer rod too high in the expansion joint, and the sealant only had at best 1/8 of an inch of bonding surface available to adhere to the side joints. Now, once the contractor cleaned out the joint, reset the backer rod to a proper depth, and reapplied the joint sealant, everything was fine. So again, all of these steps are critical to a good installation. Substrate preparation. So if you don't prepare, prepare for failure, right? That's the old saying. And it really can't be stressed enough that proper joint design is critical, but poor preparation is the #1 cause of sealant application failure. And as we say here, probably 95% of callbacks would likely be eliminated if joint prep is done correctly the first time. We need a solid, clean, dry surface to bond these sealants, and that can be accomplished in a number of ways. We can grind it, saw cut it. You can use a high pressure wash as long as you then allow it to dry. Or if it's a small area, maybe just a wire brush, and then clean the joint out. Blow it out with compressed air or brush it out. Make sure that you've got a good surface. If it's not a porous surface like concrete or brick or block, maybe, for example, it's aluminum, then maybe we just use the 2-rag method that we point out here. Wipe the surface clean and then follow with a dry cloth. We want to make sure that everything is off of the surface before we apply our sealants so that we're bonding to the proper area and not just bonding to those contaminants. So again, substrate preparation, all things adhesive is paramount. So there are 4 main benefits to backer rod: to increase elasticity in the joint sealant, to reduce excessive amount of sealant being applied into the joint, which helps to control the sealant cost, to force the sealant into contact with the sides of the joint, which again gives us a superior bond by creating that hourglass shape that we've been discussing, and to create a bond breaker, which allows the joint to be easily cleaned out and refilled with sealant as needed over time. We have closed cell rods, which are a foam material that has a surface skin. The material will not wick moisture, which makes it suitable for joints with a high presence of water or dampness. They are dense and firm and intended for outdoor and heavy duty construction. The product will force sealant against the joint sidewalls, which provides maximum sidewall adhesion. Sealants will not adhere to them, which eliminates the risk of that 3-sided joint adhesion failure. Open cell backer rod, also a foam material, does not have a skin. It can easily compress and return to its original state due to unrestricted air movement. This flexibility makes it easily conform to sealing applications and helps limit the depth of the sealant while also adding good sealant airing, which can reduce drying or setup time. We have bicellular rod, also referred to as soft rod, which is basically a hybrid between the open and closed cell rods. And it offers high compressibility, but has a closed cell outer skin to resist moisture. It's ideal for irregular joint applications where self-leveling flowable sealants are employed. And these are usually used for applications with high heat. And some of the DOTs use bicellular rods in hot joint sealant applications. Expansion joint materials, which include asphalt expansion joint, which is actually the first product our company ever produced. Then there's asphalt fiber, foam, sponge. They all react differently to our sealants. And again, the idea of the bond breaker tape or backing tape that prevents that 3-sided adhesion. Joint sealants will adhere to asphalt fiber, and that's a bad situation when we get into long-term performance of our sealants. If joint sealants become attached to the joint filler so that movement is prohibited, they won't be able to perform their intended function, which is to seal the joint against water and debris entry. So again, this is where bond breaker tape comes into play. Now, many of you have probably heard of a plastic cap product that installs over the asphalt fiber so that when we have a pre-measured depth for our sealant, but sealants may stick to that as well. So maybe we have to remember to use our bond breaker tape to prevent that 3-sided adhesion. So why use backer rod? Well, having a properly designed joint with an improperly placed backer rod is just as likely to fail as an improperly designed joint without a backer rod. So to attain proper wetting of the substrate, we want to make sure we have a proper surface and proper depth. Control the sealant depth. Again, remember that our depth should be a 1/2 inch maximum. To prevent that three-sided adhesion, sealants generally do not adhere to backer rods. And make sure that the backer rod is larger than the joint. 25% larger is kind of the rule of thumb, so that we get a good tight fit in that joint, which just makes sense, right? And this gives us a couple of benefits. If we just lay a backer rod in the joint that's loose and we don't have a good tight fit, the sealant, especially if it's a self-leveling material, might just flow around our backer rod and flow down and pour into the joint, which is not going to provide us a good seal, because now we're not controlling the amount of sealant we're using. So we're just pouring our sealant down the drain, so to speak, which is a waste of money. But if that backer rod is placed correctly, it provides us a good area for our tooling base. If it's tightly fitted into the joint, when we press our sealant into to achieve that good interface with the substrate, it will hold its ground not only to our tooling effort, but to traffic, to give us the support that the sealant needs and the adhesion to the interface that we want. Remember, the backer rod is the last line of defense before the sealant is applied. So we've got our joint, we know how to prepare it. So how do we decide what joint sealant to use? And there's plenty of them on the market, and they have all sorts of different applications. So we need to select a material to handle the anticipated joint movement, the right sealant for the right joint. Does it adhere to my substrate? Well, remember that C920 talks about whether it's glass, aluminum, mortar, different substrates. Does the joint size allow for sufficient placement of the selected materials? Expansion joints and seal joints generally have to be wider than 1/4 inch in order to get sealant in and to have it fill and move properly. So just a standard saw cut joint that you see in floors to allow for control joints doesn't really work well with sealants. Will the product perform under stated conditions of use? Does it fit my job? Not every sealant works for every application. Is there a history of application success? Well, most of the sealants you see today have been around the market for a while. The technologies are time tested. And does the manufacturer provide third-party testing? Have they gone out to reputable independent testing labs to obtain reports that certify that the sealants comply with that ASTM C920 standard that we've already talked about so much? So as I mentioned, there's a ton of different sealants out there. So you want to make sure that you're selecting the right one for your project. So first we have latexes and acrylics. And again, we're really looking at materials that should be referred to as caulk, probably not a sealant. They don't have the physical properties to match up with the urethanes and silicones and STPEs that are on the market. Relatively low movement, 10 to 12.5%. Used more as a filler for interior applications around sinks, bathrooms, etc., bathtubs, where the service life isn't as critical and we can easily replace them, and to paint over them to create that nice aesthetic that we want around our interior and exterior areas, so that we're not looking at gaps between moldings and within moldings. We can fill them and paint over them, and their cost tends to be in the low to moderate range. Butyls have been around for a long time. Solvent-based synthetic rubber materials. They have wonderful adhesive properties. They bond to almost anything, including you, if you get them on you. They don't move very well. They generally have limited movement accommodation, less than 10%. They're not as good at weathering as some of the other sealants on the market. But as I said, they do adhere very well. And you'll see them in areas where there's concerns about adhesion of the sealant. But they are hard to work with. They're stringy and hard to tool and want to stick to everything. So it makes them a little more difficult to deal with. And when you're working on the exterior of a building, the last thing you need is to get a bunch of butyl all over the place and have to remove it. The cost of butyl sealants tends toward the moderate range. Polysulfides really are considered the first high performance sealant chemistry. They've been around for a very long time, maybe not as good as some of the newer sealants, such as the newer urethanes and silicones out there, but they do have excellent adhesion. They don't recover as well as some of the other sealants. And by recovery, what we mean that when they expand, they may not contract back as well. They can be formulated for good chemical resistance. They're used a lot in commercial pool and residential swimming pool industry because they're chlorine resistant and also good for submerged applications. So you want to remember that proper priming is basically always required in those submerged applications. And polysulfide sealants often require a primer in other applications too, and they tend to be relatively expensive. So now we go from the older chemistry to maybe the newest chemistry, the STPEs, which are Solil terminated polyethers and MS hybrids, modified silicones. These are relative newcomers to the sealant world, and STPEs are becoming more and more popular in the market because they bond very well, they have good UV resistance, but they don't really work well with glass and they can't be used for glazing. But they have good weathering characteristics, not only to UV, but also to the physical elements. Great adhesion, great expansion and contraction. These products are very high solid and very low VOC. And here in California, where I'm based, the VOC capital of the world, that's definitely a very desirable trait. And the other thing that we found is that they work very well in the building envelope systems, the air barrier and air moisture barrier systems, in part because they have good physical properties, but also they're relatively benign and they're compatible with a wide variety of products. But now that I've said that, don't just go out and pick a polyether or STPE sealant to go with your weather resistant barrier system or your air barrier system. Make sure that you consult the manufacturer, because while they are fairly benign and compatible with most building materials, they may not be with yours. So again, remember what we said, do your due diligence and check with the manufacturer. Excuse me, polyurethanes, probably the most widely used sealant in the industry for a number of reasons. They're generally economical, but can't be used in structural glass assemblies. They have great physical properties. They are tough, have great expansion, great contraction, good movement capability, class 12.5, 25, and 50. Good UV resistance, excellent weathering. And as the advent of VOC regulations has become more strict, lower VOC formulas are available. They're forgiving. And most of the time when you're walking down the street and you glance down at the sidewalk and the joint is sealed with something, chances are it's a polyurethane. They're also paintable. You should consult with your manufacturer on this, but in trying to paint over any of these high performance sealants, it's important to understand that these sealants are designed to move. And if we're going to coat them with something, that coating or paint should also be designed to move. So let's think about that for a minute. If I take a sheet of rubber and I paint over it, and then I bend it, and if I've just used a regular standard latex paint, that paint is going to crack when that rubber moves. Or if I expand the sheet, that paint's not going to be able to move with that expansion. And eventually the paint's going to come off of that sealant. So again, if you're going to paint over these sealants, make sure that you're getting the right material to coat them. Silicone is not necessarily a newer technology, but a very high performance technology. The silicones adhere to a wide variety of substrates, glass. They're used for glazing and structural glazing, concrete, wood, all sorts of different things, and generally do not require a primer, although in some circumstances a primer could be recommended. Excellent UV resistance and great weathering capabilities. And they can have good chemical resistance and temperature resistance, and they're good for sealing the perimeter of fenestrations. Generally are not paintable. Really not much sticks to silicone. They have the highest movement capability, class 50 to 100, generally longer service life and continued flexibility over time. But silicone sealants can have strong odor and take considerable time to fully cure. And cost for the silicone sealants is generally in the high range. So which one should I use? Well, as with most building materials and product decisions, the answer is it depends. But the goal is to determine the best sealant for the application and compatibility to the substrate, budget, service life, etc. So this is a nice quick reference chart that does, I think, a really good job of showing which sealants might be suited for which applications. If you'd like to take a picture or a screenshot of this chart, please feel free, or feel free to contact us afterward, and we'll be more than happy to share it with you. And note that we have a rating system at the bottom to help determine suitability. And these sealants are listed in the same order that we discussed them, from latex across to the higher performing polyurethanes, silicones, and the STPEs, which fall mostly into the excellent category, with most of the uses that are listed here. And I would suggest that you keep this chart close by when you're starting to explore different types of sealants and what your best options are likely to be for different applications. Now, there's a lot of good information here, but remember, this is just a guide and hopefully serves as a starting point for you. But you might want to talk to your manufacturer's rep and get some help in dealing or deciding what might be the best product for your specific application. So again, talk to your trusted reps and pick their brains. Installation, another part of our designing for success. This slide illustrates some of the failure possibilities associated with joint design, in many cases being the result of improperly placed or selected backer rods. So let's start with number one on the right-hand side here. We can see that this is an example of proper joint design. Our width to depth ratio is correct. The sealant is tooled properly, and the backer rod has been placed to the proper depth. Exactly what we've been talking about all along, right? Now, our adhesive and cohesive failures go way down in predictability when the joint design and sealant application is done correctly. The sealant needs to be gunned in at the middle of the joint, so that if it's a self-leveling material, the sealant will flow out properly, and if it will need to be tooled, the sealant is evenly gunned in. Now, I showed a photo earlier in the presentation where we saw a nozzle being set in the middle of the joint and the sealant being installed evenly. Not only at the width of the joint, but also throughout the entire length of the joint. So in examples 2 and 3 here, these are the things we want to avoid. Example number 2 here, we're adding too much depth of sealant in our joint design just by pushing our backer rod in too deep, which means we have lost that proper width to depth ratio we want. So now we have a good chance of adhesive failure, where the sealant wants to pull away from the sidewalls. And looking at example 3, this is kind of the opposite issue of example 2, right? Instead of too much depth of sealant, now we don't have enough. The sealant is just too thin and too shallow across the joint to develop the cohesive strength that we need, and can end up tearing across the middle of the joint somewhere, as we see here. And that goes back to our discussion of cohesive failure, right? So in this case, that backer rod did not get set deep enough into that joint. And I love this graphic because it shows these examples side by side, so that you can actually see the differences between a good, proper application and poor applications. And above that graphic is a shot of someone placing backer rod by hand. But next to that is an example of a tool that can be used for putting that backer rod into the joint and setting it at the correct depth. And there's many versions of these tools on the market that contractors use, from small handheld to walk behind versions. But mainly, I just wanted you to make all of you aware that these tools do exist, and experienced qualified sealant applicators are used to using these tools to help them do their job. Priming. Priming, the intention of using a primer is to improve the bond of the sealant to the substrate. Priming is almost always required in submerged applications, and sometimes in horizontal applications as well. But keep in mind that priming is not a substitute for good prep, okay? The primer can only be as effective as the condition of the substrate allows it to be. In this joint application, you can see that they've placed blue painter's tape on each side of the joint, which can help to keep the primer from contacting the surface above the joint and can serve the same purpose when the sealant itself is later applied, to help set a nice clean line with no overrun out of the joint, kind of like using painter's tape when you're painting a wall to keep a nice straight line. And if a little gets on the tape, it's okay, because you'll be peeling the tape off later anyway. And for less experienced applicators, This is a good way to learn to apply the sealants until you get the hang of it, kind of like training wheels, so to speak. Also, for proper primer application with a brush, like we see here, you want to prime both sides of the substrate or both sides of the joint without getting it outside of the joint and onto the substrate, which could cause staining, which can be a real pain to have to clean up. And you want to prime and apply your sealant the same day. And further to that point, always go by the manufacturer's priming instructions, which can vary. Sometimes if you apply the primer and leave it for too long before applying the sealant, it loses its priming ability, and in some cases, it even becomes a bond breaker. If it dries, it can actually prevent the sealant from adhering. So if the instructions say all primed surfaces must have material applied within 24 hours, for example, then you either need to adhere to those instructions, no pun intended, just a little joint sealant humor there to see if you're still awake, or you may have to reprime the joint the next day before you apply the sealant. And then an adhesion test. Include a note in your specifications that we want to do a test on the site for adhesion. The field adhesion test is simply a hand pull test of a cut area of joint sealant. And we're not going to get too much into detail on how the test is performed, but there are YouTube videos of the adhesion test being done that you can take a look at. So if anyone is interested in seeing the actual field test performed, take a look at one of these videos. Also, the pull test is a good indicator of the fundamental adhesive properties of a sealant on a particular substrate. So we want to first apply our sealant to the substrate and let it cure, because curing is important so that it's not just dry, but has been allowed time to develop its full adhesive quality. And then we're going to pull the sealant back. And as the diagram shows here, we are looking for cohesive failure. We want the sealant to rip right down the middle, and hopefully leaving the adhesion to the sidewalls intact. So if our application passes this test, we know that the joint was cleaned properly, the backing material was placed properly, and that we're going to have a long service life of the sealant. So guide specification for elastomeric joint sealants. Some sections to consider. 1.03, to reference our ASTM standard 661, different sorts of things. In their quality assurance, does the manufacturer have experience? Does the installer have experience? And make sure you're specifying products, sealants, and primers that meet local VOC regulations. Materials, well, this is where our C920 comes into play, right? So do we want a performance specification and you have to meet this alone? You want to make sure you're getting a silicone if you want a silicone, because just C920 may not be enough to indicate that you want a silicone and would otherwise allow for, say, a urethane to be used, for example. Accessories. Do we want a primer? Do we want a backer rod? Let's make sure the accessories that you want are listed as well. And then the all-important joint preparation, 3.02, that we've been discussing throughout the presentation, right? We want to make sure we define the preparation that's expected. And that might be as simple as saying, joints should be prepared as per manufacturer's written instructions. And that's fine, just as long as joint prep has been accounted for and addressed. And again, as we mentioned earlier, 95% of a successful application is having proper joint design. So we've covered a lot of ground today, right? So in summary, we've learned that joint sealants are an important part of the performance and longevity of a building. We've looked at the difference between a sealant and a caulk in terms of performance characteristics. And as we discussed earlier, latex and acrylics tend to fall into the caulk category, which are best used on interior applications. And when we get into critical parts of the building, we want to use a sealant. At the job site, slow down the process to make sure that everything we've talked about has been done, from joint sealant design to prep and finally to installation of the sealant. All of these factors are critical in helping to ensure a successful application. So as we've said today, there are many different types of joint sealants out there on the market, and we've tried to give you some of the information and tools that you need to decide which is best for your particular project. And again, not everything works for everything. And lastly, you now have the information you need to do what many of us do who are joint sealant manufacturers, which is to annoy your family and friends by looking down as you're walking along and notice the condition of the sealants you see, and notice if they have failed. And if you really want to impress them, now you have the tools to explain in some detail why and how that joint failed, just in case they were wondering.